Welcome back. So, as we've seen so far in Chapter 8, when we consider electrons, these very tiny particles, we understand that they have this dual nature, right? This wave nature and this particle nature. And based on the work of de Broglie and Heisenberg, we know that we can't understand the behavior of these electrons or quantum particles in exact detail, right? So what Heisenberg told us and what's been demonstrated is that we can't know both the position and the velocity of the electron. We can only know a probability of where that electron is going to be at any given time. So we can generate what we call probability maps to define where a given electron of a certain energy will be located. Now, these are what we eventually will understand as orbitals, these probability maps. And these orbitals were described by using Schrodinger's equation. So Schrodinger is the one credited with coming up with an equation that can be used to solve for the various probabilities and areas of space where these electrons can be found. And Schrodinger's equation, which is the form of it's listed here, allows us to generate what are called wave functions, right? That wave particle of the electron, and these wave functions eventually will allow us to generate what we know as the orbitals, which again are just simply probability maps of where we can find an electron of given energy around a nucleus. And so if we look at sort of where we are here, we have the energy and the velocity are directly related, right? And so electron energy and position are complementary, right? So we know that position and velocity are complementary. And since velocity and energy are related, right? We know that from simple equation like kinetic energy equals 1/2 mv squared, right? Velocity and energy are directly related. And so that means the energy of the electron and the position are complementary, meaning the more we know about the exact position, the less we can know about the energy, and vice versa. So if we know the energy of an electron, so if we define the energy of an electron, we can only know its position with a probability, right? We can describe its position as a region of probability. So this is where solving Schrodinger's equation comes into play. Now, we will in no means attempt to solve Schrodinger's equation. It is what we call an operator. And so there's many solutions, right? It's like doing a function on a function, kind of like you do a derivative, right? If you are an integral, right? If you're conducting a mathematical function on a function. But there's many solutions, and each of these solutions can then give rise to an orbital, right? Or again, a probability map describing where an electron of a given energy can be located around the nucleus of a given atom. And so the solutions to this equations give us these wave functions, and we generate the map by plotting distance versus the wave function squared, and this gives us these three-dimensional maps, which we're going to refer to as orbitals. So this is about as good as we're going to do here, right? We're not going to dive a lot deeper into this. But what I'm going to do now is I'm going to go a little bit out of order of what the book does. And so the first thing I want to do is describe the orbitals in general. So what are the different types of orbitals? And then I'm going to skip ahead a little bit into chapter 9, and I'm going to talk about something called electron configuration, which describes sort of how we fill the orbitals with electrons. And then I'm going to come back and talk about the idea of what we call quantum numbers. Okay, so orbitals. So again, an orbital is a probability map, a three-dimensional area of space where an electron of a given energy and certain properties are likely to be found. And so what we see here on the right is a picture of all of the possible orbitals. Now what we're looking at here are the orbitals that can be all possible. Now, of course, not every atom is going to have all of these orbitals, or they're at least not going to need all of these orbitals based on how many electrons they have. So we're going to look through these in a little, just as an overview, and describe some of them in a little more detail. So we have what are called s orbitals and p orbitals. So s orbitals are spherical, right? And they come in sets of 1, right? P orbitals are peanut shaped, right? Try to use some alliteration here for P for peanut. And they come in sets of 3, right? Where there is a 2-lobed peanut along each of the 3 axes, the x, the y, the z axis. Now, one of the things that we understand before we get too deep into this is that all orbitals, no matter whether they're an s, a p, or any other type of orbital, can only hold 2 electrons. So every orbital is a 2 electron orbital. An s orbital is present at every energy level. Now, we'll get back to these when we talk a little bit more about quantum numbers, but the energy levels can be thought of sort of like the numbered levels when we talked about the Bohr model, right? So these are at different distances away from the nucleus. So at every one of these levels, there's another s orbital. Now, p orbitals are higher in energy than s. And again, they come in sets of 3. And the p orbitals are present in all of the energy levels at 2 and above. So the first energy level does not have any p orbitals. It only has an s. At the second energy level, it has both an s and a p. So if we look at some of these functions, just to kind of give us an idea. So this is the 1s orbital. So this is the s orbital on the first energy level. And what we see here is if we plot distance from the nucleus versus probability, what we see is that this electron is very likely to be located very close to the nucleus, right? About 53 picometers from the nucleus is the maximum probability of finding that. So the electron is likely to be found right in this sort of area. If you look at the same kind of plot for the 2p orbitals, and this could be for any of these, they're going to be similar, just on the different axis. You can see here that your maximum probability now is located right about 200 picometers, right? So again, this is in the first energy level, this is in the second energy level, right? Located further, the electron is likely to be located further away. Now you notice there is some probability that it's going to be located, again, very close. So your 1s is going to be somewhere in here, and there is a small probability that this electron could be located, only say 100 picometers or even less. But the vast majority is going to be between 2 and all the way out to, say, 450 picometers, right? So again, these are probabilities. And it's going to be located within the areas defined by the shape. Okay, so we got S and P orbitals. Now, as we move further away from the nucleus, now again, remember, we're moving outward, so there's going to be more physical area, right, volume, as we get further away. So as you move further away, we get to more kinds of orbitals that are possible. So we have D and F orbitals. So again, these are all 2 electron orbitals. D orbitals come in sets of 5. So they are higher in energy than the P orbitals. And F orbitals are higher in energy than the D orbitals. D orbitals start at n equals 3. So if we're sort of going along, right, at n equals 1, we have just S. At n equals 2, we have S and P. At n equals 3, we have S, P, and D. When we get to n equals 4, we have the possibility of having all 4. And again, as we go above that, then we continue to have all 4. Now, the d orbitals, I do want you to understand something about the characteristics here. Most of them, at least 4 of them, are what we call double peanut shaped. So it's like having sort of 2 p orbitals, right? 4 lobes, we'll call them double peanut. Now, 3 of these, right, this one, and this one, have the lobes located between the axes in different planes. So we have the DYZ plane, right? So this is located in the YZ plane with the angles with the lobes bisecting the axis. We have one located in the XZ plane, and we have one located in the XY plane. So these 3 are sort of related to each other. And then we have the dx squared minus y squared, which looks the same as the dxy, but has been rotated 45 degrees, and the lobes follow right along the x and y axis. Now the 5th one is a little bit different shape. It's the dz squared. It's along the z-axis, but it's just 2 lobes and with what we call a toroid or a donut in the middle. So it looks kind of different, but it travels right along the z-axis. And so those are your 5 d orbitals. Now, the f orbitals, I'm not going to have you know the names of them, but we want to understand that most of these are more complex. A lot of them have up to 8 lobes, and you have a set of them that are like the dz squared and have those toroids in them. And there's, of course, 7 of these. So 5 here, 7 here. So we have s orbitals, p orbitals, d orbitals, and f orbitals. Now again, each of these orbitals comes from solving Schrodinger's equation, right? Is a different wave function, a different solution for Schrodinger's equation with different inputs. So different energy of the electron, etc. are going to give rise to these different orbital shapes, these different probability maps. So we've talked in general now about these orbitals and their relative shapes and sort of a general idea about, their energy relationships when they're on the same energy level. Now, let's talk a little bit more about why this happens and more specifically about the order that the orbitals will fill up. Now, a couple of things to remember is the closer you are to the nucleus in an atom, the more stable an electron is going to be. So electrons want to be as close to the nucleus as possible. That's going to be lower energy, higher stability. But of course, not every electron can be close to the nucleus because all of these orbitals can only hold 2 electrons, and so you're going to have to move further and further away as you put more and more electrons into an atom. So as you start getting up to electrons that have more than 1 electron, so anything above hydrogen, right, you have this need to occupy multiple orbitals. And so it's important to understand the relative energy of these orbitals. Now, if we look at this graph here, this can demonstrate something called penetration of the orbitals. So this is one of those distance from the nucleus versus probability of finding an electron. And so first of all, this thing right here, this is the 1s, right? And so this has almost all of its probability, again, really close to the nucleus. Now, as you move to the second level, remember you're going to have a 2s orbitals and you're going to have 2p orbitals. So at the second energy level, you have both s and p orbitals. If you look at the s orbital, in red here, you see that it has a lot of its probability out here, right? But it has a not insignificant probability that is really close and penetrates into the area occupied by the 1s. This stabilizes the 2s orbital and makes it lower in energy than the 2p, right? So it's this idea of penetration of the probability, the probability of finding the electron. There's a higher probability of finding this 2s electron closer to the nucleus than there is for the 2p, and so it gets a lower energy. And it means it's going to be more stable and the electrons are going to occupy it first. So if we consider both the 2s and the 2p, we see that the 2s is lower in energy, so electrons are going to fill the 2s before they start to fill the orbitals of the 2p set. And it all has to do with where the electrons have a higher probability of being. So because there is this area of probability very close to the nucleus for the 2s, then it's lower in energy compared for the 2p, where its probability is a little bit farther away. So it's really this thing here that causes the 2s orbital to drop down in energy. And as we go up, we start to see this pattern. So as we go up to the 3s, or the 3 level, right, we see the 3s, the 3p, the 3d. And as we said, the s is lower than the 3p for similar reasons, and the p is lower than the d orbitals, the set of 5. Again, similar for these reasons of penetration, right? That the electrons in these orbitals are going to be closer to the nucleus, then thus lower in energy, more stabilized. And so this is going to be a region where electrons are going to want to be. They're always going to want to be in the lowest energy area. Now, as you get up here, what you notice is the energy gap starts to get smaller and smaller. So there's a big gap between the 1s and the 2s, and even a pretty good gap between the 2s and the 2p, or the 2s and the 3s, if you will. But as you start getting up here into the 3rd and the 4th, right, these things start to get closer and closer. And so as they spread out, so the 3s drops down, and 3p and the 3d, and then you get the orbital, the s, the 4s, the 4p, and then the 4f, which are not pictured, right? These things start to cross over. And so what you see here is that the 4s is actually lower in energy than the 3d. And that means it's going to fill first. Even though it's at a higher, quote, energy level, the energy of this particular orbital is lower than the 3ds. So the electrons don't care. They're going to fill that lower energy orbital first. And this is the pattern that we see, is that the s orbital of the higher energy level drops below the d of the lower one. And so the 4s fills before the 3d, the 5s fills before the 4d, etc. And so we get this order of filling, right? And the nice part about it is the order is always the same. So I could just write this out, right? We fill in the order of 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and I'm just following along, right? 5s, 4d, etc., right? Now, there's lots of ways to think about this. You can memorize this order, you can do other things, but I think by far the easiest way to think about this is to understand how these things work when you overlay it with the periodic table. Because remember, you're just putting electrons in there, so as you get bigger and bigger atoms, you add more electrons, right? So as you go every one step on the periodic table, that's one more electron. And so as you go, every time you go over, you have one more electron, and it's just going to fill. And it's going to fill following these orders. So if you plot this and you overlay it, what it turns out is that every time you're in group 1 and 2, you're filling an element in group 1 and 2, you're going to end filling an s orbital, or putting electrons into an s type of orbital. When you're in groups 3 through 8, or the other part, this group of 6 columns here, you're always going to be putting electrons into a p type of orbital. This is called the p block. As we're transversing the transition elements, right? Notice there's 10 columns. You're going to be filling the 10 electrons that will occupy the 5 orbitals in the d set, or the d block. Notice the drop, right? This is the product of this crossover, right? That you're in the 4th period and you're filling the 4s, but then you fill the 3d because that 4s is lower in energy. And then finally, the f orbitals will fill after the 6s and the 7s. So remember, they come down here. Right? If you remember the periodic table, they fit right into there. And so they're going to be sandwiched here between the 6s and the 5d, and the 7s and the 6d are going to be your f orbitals. But if you can use the periodic table, which you always have access to, and you just know that, the first 2 electrons for hydrogen they're always going to go in the 1s, right? The next 2 are going to go in the 2s. Then the next 6 are going to occupy the 3 orbitals of the 2p. And you just keep going, reading across the periods and filling up and following this order. So by using a combination of just understanding how the orbitals work together in terms of their relative energies and how they interface with the periodic table, we can lay out how the electrons will occupy the orbitals for any element in the periodic table.